Hello, good morning, students. So, today we will continue with the elemental analysis technique. Previous class we discussed in detail about proton-induced X-ray emission spectroscopy. This time we will come across another important technique used in elemental analysis. Okay, so that is on neutron activation analysis. So here instead of protons, uh, neutrons are used as projectiles. Okay, neutrons are used. So making use of neutrons, high energy neutrons, or we can say some certain specific energy. Okay. So in neutron activation analysis, we prefer certain type of neutrons. So neutrons of varying energies are available, but here we will prefer some specific range of energy. What energy we will soon very soon. Okay. Uh, so, uh, so in fact, this neutron activation analysis, or abbreviated as NAA. Okay, NAA. Okay. So it was initially started. The theoretical framework done by George Havasi, basically Hungarian chemist. Later became German. He's a Nobel Prize winner too. So he was the pioneer in designing such a technique, neutron activation analysis technique. Okay. In 1936. Anyway, still many other physicists contributed in the improvisation of neutron activation analysis. In the modern scenario, it's a very ultra-modern, highly sophisticated, very precise nuclear technique to identify different elements. Okay. Almost around 80 elements in periodic table can be very conveniently identified by using this technique. Okay. So this got improvised. Even though it designed in 1936, the technique was more improvised after neutron was easily available in nuclear reactors. Okay. From reactors, by certain reactions, neutrons can be produced. Neutrons of requisite energy can be produced. So after that, this technique became more handy and more popular. And as I told you, we use a specific type of neutrons called thermal neutrons. Okay, thermal neutrons are of certain range of energy. Uh, Very soon we will classify the neutrons, and we will see what kind of neutrons are actually thermal neutrons. We will find it definitely. Okay. Anyway, thermal neutrons are now, just understand that we make use thermal neutrons. These thermal neutrons are bombarded on your element of analytical interest. So certain sort of instability may come, and that instability leads to the disintegration of the nucleus, which may emit certain characteristic radiations. Okay, that will be recorded and analyzed. So neutrons, as you know, they are charge neutrality, so it provide with high penetrating power through materials, and hence better for analyzing both thick and thin samples. So it is very clear. Okay, neutrons are chargeless. So irrespective of your sample is thick or thin, neutron can comfortably pass through it and hit the nucleus of our interest, and they may produce requisite reaction, nuclear reactions. So that is our aim. So unlike in Pixie, here your sample may be thick or thin, it doesn't matter, we will get our desired signals. Okay. So neutrons undergo elastic and inelastic condition in the targets, and here inelastic scattering is suitable for chemical analysis. So, you know, if the scattering or collision is elastic, then no energy transfer takes place. So the target nuclei does not undergo any sort of change, any sort of instability. So we always prefer inelastic sort of scattering. In inelastic scattering, a part of the energy of the neutron may get absorbed, or neutron itself may get embedded, or that we call neutron capture, by which nucleus accept the neutron, incident neutron. So there comes a sort of energy disequilibrium inside the nucleus. So nucleus become unstable. So that leads to the emission of certain sort of characteristic radiations. So that word is very important. We prefer or we expect certain characteristic radiations out of the nucleus on collision with the neutrons. So another important feature is that it's a multi-elemental technique, in the sense that the method, the technique can be used to identify so many elements at a time. Your sample may contain many elements of your interest. All those elements can be simultaneously analyzed. This is an important feature of any ideal elemental analysis set, as we outlined in the module 1. As well as it is highly sensitive too. Keep in mind, it is highly sensitive in the sense that it can identify the sample, it can identify the element of interest even if it is present in pico or nanograms. Okay, even at low level, picogram also identified. Picogram means 10 raised to minus 12 gram. Okay, this is extremely small value, still identifiable using this technique. It's a striking, interesting aspect of nuclear activation analysis. And what is happening is the kinetic energy of the incident neutron is taken up by the target nucleus and undergo excitation to its characteristic excited levels. So this is a typical arbitrary diagram shown here. These are all nuclear energy levels, not the atomic energy levels. So once a neutron gets impinges within the nucleus, there are nucleons, enough number of nucleons, protons, neutrons. So the collision may lead to the excitation of the protons and neutrons to different nuclear energy levels. So their redistribution after the collision may be according to certain quantum rules. Okay, definitely. So they cannot go in any arbitrary energy level. They have to go to certain well-defined quantized energy levels within the nucleus. So that depends on the inherent nuclear energy level of the sample. So from where they may make transition to the respective lower states. So these are again quantized and unique for a particular sample. These are unique, again not arbitrary. So the transitions are also unique. In other words, it implies you get unique unique fingerprint photons. Okay, they may lead to emission of 10 nuclear photons. That means gamma rays. Gamma ray photons are emitted. They are unique for a particular sample. Just like when you take the atomic spectrum of a sample, that is unique for a sample. Similarly, same wise, here also nuclear energy levels and the corresponding nuclear emission photons, I mean the gamma ray photons, are unique for a sample. No two different elements can have identical nuclear radiations or gamma rays. Or you can even talk about the emitting protons, alpha particles. They will also have unique energy. So that corresponds to their fingerprint, nucleus fingerprint. So no two persons can have identical fingerprint or DNA print. So very similar to that. So subsequent de-excitation results in the emission of characteristic gamma ray photons due to this bombardment. Okay, that is called N-gamma reaction. Neutron is impinging on it and gamma is emitting out. So that's the meaning of N-gamma reaction. Neutron is the projectile and the outcome is the gamma ray. Okay, so for which what we have to do, target should be exposed to high thermal neutron flux. So imagine that the neutrons are coming in thousands and thousands or millions and millions, just like a light beam. You can imagine the neutron flux coming over to the sample is similar to a laser beam. In a laser beam, you have photons, light photons. Instead of that, here you have neutron flux. So neutrons are, you can imagine, less like light photons. Okay, and the energy is specific. Okay, as I mentioned earlier, we prefer neutrons having energy in the range of 0.025 electron volt, and the expected thermal flux, neutron flux is 10 raised to 10 centimeters per second. That means in each second, it implies that in each second, how many protons are crossing, how many neutrons are crossing? 10 raised to 10 neutrons crossing per second through 1 centimeter square. So if you expose for a few milliseconds or for a few microseconds, you can imagine how many neutrons fall over the surface. Okay, and you know this energy, the neutrons with 0.025 electron volt are known as thermal neutrons. Okay, we will very soon see the classification of neutrons. Then you will understand much more about the neutrons. And another interesting, striking feature of the NA technique is it is possible to quantize around 74 elements in the periodic table with this techniques. Okay, so these are some of the typical elements that are being that are being quantified or analyzed using the NA. So it's still there are 74, and the exhaustive list of the entire 74 elements are shown, beginning with dysprosium, europium, like that, ending up at lead and sulfur. Okay, so their sensitivities are given. If dysprosium is present even at 1 picogram, they are analyzable. That's the meaning of this. And you see the bottommost level. Lead is identifiable if they are present in 10 raised to 7. That means around 10 raised to minus 5 gram. Even if they are present at 10 raised to minus 5 gram, they are identifiable. So sensitivity differs. The table implies that the sensitivity of the element vary from element to element. Still, around 74 elements are identified. That's a very blessing side, the positive side of the neutron activation analysis. Okay, so they are symbolically shown here in the periodic table. It extends from all periods, all groups, and irrespective of the groups or periods. And some few remarks about the neutrons. You know, free neutrons are not stable. They can easily decay away to give protons and electrons. These are all fundamental things you have already aware about, and they have highly affinity to react with surrounding materials. Okay, the moment they transfer to any either in gas or in any solid material or in liquid material, they start reacting with the neighboring particles or atoms or nucleus, highly reactive. That's another property. So even exposing neutron to human body is very dangerous because of their high reactivity. And on neutron capture, an analyte nucleus gets converted into an isotope with the same atomic number but with the mass number greater by 1. So mass number increased by 1. And so that is what leads to instability. The new nucleus is in a highly excited state because it has acquired about 8 MeV of energy by binding a single neutron. So that is the very reason. The 8 MeV energy received by the nucleus leads to the instability. So that is the very reason for the emission of other radiations. Okay, the cause and effect relation, you can say. Cause is the bombardment with the neutron, and effect is the emission of characteristic gamma radiation. And excess energy is released by prompt gamma ray emission. So it is not mandatory that always you may get a prompt gamma ray emission. There may be delayed gamma ray emission too. Prompt means there will be a simultaneous emission of gamma ray the moment neutrons are bombarded. And in the delayed gamma ray emission, gamma ray may get emitted after a period of time. Okay. So and it is not always mandatory that gamma rays emitted. There may be emission of protons, there may be emission of alpha rays, like that. Okay, so that is also the probability. And anyway, prompt gamma ray emission by neutron capture is of analytic interest. It's a most interest in our context. Okay. There may be emission of protons, alpha particle or beta particle. That we are not our concern. Those things are not our concern. So here is a few remarks about the neutrons. We can classify the neutrons according to the energy. If the energy is ranging from 0 to 10 raised to 3 electron volt, we call them as slow neutrons. Slow, okay. And the next class of neutrons are intermediate neutrons. Their energy ranges from 10 raised to 3 eV to 10 raised to 5 eV. And we have the third class called fast neutrons used in nuclear reactors, 0.5 MeV to okay, 10 MeV. And we have the fourth classification, very fast neutrons, whose energy varies from 10 MeV to 50 MeV. And you have the last class, that is called the ultra fast neutrons. Their energy is above 50 MeV. Okay, so each class is of different applications, and the second class are of no application. But in which we will be concerned with the first class, like the slow neutrons. Slow neutrons are again subdivided into a few categories. So that is what we are going to see. The slow neutron, as you already mentioned, slow neutrons energy vary from 0 to 10 raised to 3 eV. And it is subdivided into first class is called cold neutron. Their energy is in the range of 0 to 0.002 eV. And we have the most important class of neutron called thermal neutrons. Their energy is in the range of 0.025 eV. That is what we are concerned with in our neutron activation analysis. And third class is epithermal neutrons. Their energy is less than 0.5 eV. And we have the fourth class called resonance neutrons. Their energy ranges from 1 eV to 100 eV. Okay, so out of which only we are concerned with the thermal neutrons having energy 0.025 eV, and with which our entire analysis is done. Okay, so as you already know, the typical schematics of a neutron collision reaction. Neutron on impinging on the nucleus of an analytical interest, it excited and its mass number changes, resulting in the emission of a gamma ray. So it is not mandatory that always gamma ray is emitted. Gamma ray can be two gamma ray can be emitted, 3 can be emitted. That anyway depends on the property or the nature of the nucleus, and resulting in the creation of certain other daughter nucleus, products, you can say. And we are concerned with the gamma. What is the energy of the gamma and how many gamma photons are emitted? Energy or the frequency will lead you to the type of target, and the quantity of photon, the number of photons will lead you to the amount of that target, how many number of nuclei is present. So this is a typical arrangement for a fixie, and anyway we will come to the detailed experimental technique later. Neutrons are focused here and allowed to deviate using a graphite diffraction crystal, and a tightly focused neutron beam is allowed to impinge, incident on the target, and target results in the emission of gamma ray. This is a gamma ray spectrometer in which the energy of the gamma ray will be recorded, energy as well as intensity will be recorded. Usually a high purity germanium semiconductor detector is used for this purpose. Okay, these are all surrounding things are all concrete, high, thick, strong concrete walls, because neutrons, highly dangerous if pass through the human body. So enough sufficient precaution has to be taken, usually done in highly sophisticated nuclear laboratories. Okay, so that is what is shown here. And there are two classes of nuclear activation analysis according to the method. One is called the prompt nuclear activation analysis, and the second one is called the delayed nuclear activation analysis. So where we prefer prompt nuclear activation analysis, this is preferred where the activity is short-lived. That means those nuclei whose activity is very fast, disintegration is very fast. That is what is called short-lived activity. where as soon as the radiation is over, we have to carry out the counting, gamma ray counting, because activity may last a few seconds, few microseconds, or few milliseconds, or say a few minutes. So gamma ray counting has to be done within short span of time. So that is what is called prompt nuclear analysis. And we have a long-lived analysis too, where counting will be done after a radiation sample for a long period of time. Suppose the half-life of a sample is say 1 year, 2 year, or 1000 year, then we can resort on long-lived or delayed nuclear activation analysis. So this is also called offline analysis, in which sample is exposed, sample develop enough activity, enough instability, and the decay starts after a while. Okay, so then we prefer delayed nuclear activation analysis. So this is the second class of nuclear activation analysis. And here a typical schematic is shown, a decay diagram is shown of cobalt. You can see what type of gamma rays are emitted, what type of other radiations are emitted. So it is obvious that the emission of beta is irrelevant. Okay. Once you know the emission of gamma ray of this much energy, 1.17 MeV energy, then we can finalize that the element of interest is cobalt. So there is a uniqueness for the energy of this gamma ray, either 1.17 MeV or 1.33 MeV. This is unique for cobalt. So that is how the element of analytical interest is identified. If the gamma ray energy is of something else, you can conclude that the element is something else, not cobalt. So that's a methodology involved in identifying the sample. And according to the procedure, neutron activation analysis can be either radiochemical separation neutron activation analysis, what's called RCS, or purely instrumental neutron activation analysis, PAE. So what is the difference between these two? Let us see. It is only differ in the initial procedure, initial sample preparation. According to sample preparation, you have classified into these two. What is called radiochemical separation, in which what is done actually is first the sample is irradiated. Okay, this is preferred when the element of interest is very small in the sample. Suppose you have a coal sample. Coal sample contains very micro or trace level of uranium example. Then what is done? You initially irradiate the sample with some neutron flux. Thereafter, what happens? The uranium may start, or any other sample, any other nucleus may start emitting the radiation. If the content is too small, what may happen? And the matrix is of high value, the amount of matrix is too large, then the emitted radiation may get absorbed by the matrix. Emitted gamma ray photon may get absorbed by the sample. So then it becomes difficult to detect the gamma ray emission, because emitted gamma ray is absorbed by the matrix. So what is done after radiation? Some sort of chemical reaction is carried out, some chemistry is carried out, and the matrix is removed through chemical reaction. Okay, suppose you have a sample of some sand, some sandy material. Suppose it contains some thorium. By suitable chemical reaction, other elements, all other elements other than thorium, is removed through some chemical action. Then the resulting sample will contain, the residue sample may contain only thorium, mostly thorium. Then it is very easy to analyze them by keeping in a gamma ray spectrometer. Okay, instead if we prefer the entire matrix, then what may happen? The emission from the thorium may get absorbed by the matrix, and there will be nothing left for the identification inside the gamma ray. So the purpose is simply to make the concentration of the element of interest high. Okay, in order to increase the concentration of the element high. So okay, when the activity of the matrix strongly interfere with the determination of the trace element, we prefer RCSs. So here what is done, the desired trace element is extremely weak in activity, then we prefer this method, and then trace element of interest needed to be concentrated after radiation. So for which what is done, suitable carrier is added to the ready sample to remove a particular element of interest or a group of element of interest. Okay, so that carrier will make some reaction uh, with the element of interest and they form stable compound. That stable compound you can remove from the matrix. So that is the mechanism. The separate element is then counted for gamma ray activity. So because now amount concentration is large, so gamma ray activity will be also proportionally high. So chemistry is performed after radiation, hence no contamination occurs before radiation. Okay. So only those nuclei will be activated which are of interest. Okay, that is why chemical action is performed after the irradiation. Otherwise, what may happen? Many other elements may also get exposed and they may also get excited, and their radiation may also be there. So there is interference. Okay, that can be avoided. Now, the next method, second method, sample preparation is very simple because we don't execute any chemical action here. The sample is directly taken, activated by neutron radiation, and then counted for gamma ray using a gamma ray spectrometer after a suitable decay time. So this method is non-destructive. Why? Because sample is not undergone or sample is not subjected to any sort of chemical action. So that's why it is called as non-destructive. So it is more preferable if possible because sample is not destroyed. So you can keep safely the sample for later reference. Okay. So you can schematically show these two methods. First, what is done? Simultaneous radiation of sample and standard. You are simultaneously radiating, and if it is a long-lived process, you can keep it for a while. It's called cooling period. Okay, sample is allowed to undergo sufficient excitation, then emission. And if it is a non-destructive method, you can directly take it for counting of gamma ray, and gamma ray emission is analyzed using your data processing units. Or if the sample of interest is too small in quantity or trace level, you have to depend on the destructive route. You make the chemical action here, separate the element of interest, then do for the gamma ray counting. Okay. Subsequently, signal analysis for finding energy as well as the intensity in gamma ray. So these are the different routes to perform neutron activation analysis. So we have today introduced the procedure. Only the introduction part we covered, and in the next module we will talk about the detailed instrumentation, how this is carried out in actual practice. So here is a small question: distinguish between prompt and delayed neutron activation analysis. Comment on the applicability of each. So you do certain Google search and find out where you can apply prompt analysis and where you can do delayed analysis. What type of materials? Okay, you take some survey on some literature, either in books or in internet sites. Okay, or include in your notes along with the definition of prompt analysis and delayed analysis. So with these remarks, let us conclude today's discussion. Okay, thank you all of you. Have a nice day.